things that are going on in the um, the Heliophysics Big Year has a bunch of themes. Each month is a different theme that has something to do with the sun. And the February theme is fashion. I'm very sympathetic to you all. You're going to be taking fashion advice from a male astrophysicist, but I'll do the best I can to make this an interesting subject instead of, well, a dismal failure, I suppose. Heliophysics and astronomy is sort of, at NASA, is sort of based on three big questions. What causes the sun to change? How does the Earth and the heliosphere react to these changes? And what are the impacts of these changes on human technology and operations in space, and also operations on the ground? To make this a more palatable subject for formal education in K-12, we've created a framework for heliophysics education, which shows how heliophysics concepts map into a variety of science standards and some math standards as well. So you can teach these standards by talking a little bit about heliophysics, which is actually a subject that's missing from the science standards, as is the fact that the Earth has a magnetic field. So we try to make up for that by showing how to basically matrix these very important concepts back into the national science standards. So here they are, variety of sub-questions under each of the three NASA heliophysics questions. And each of these sub-questions are connected up with at least one, if not more than one, science standard. So it makes for a very quick read. If you go through this PowerPoint and look at this particular slide, you'll have a good idea of how the framework operates and how it operates within the context of these big questions. Okay, now for what you've all been waiting for. Fashion, color, and light go together like a glove and a hand, right? I mean, you wouldn't have a whole lot of interesting fashion without some color thrown in. And once you start talking about color and light, well, then you're talking about physics. And I gotcha. You can't turn back. So what we're going to do in the next 50 minutes or so is we're going to talk about how color is produced, and also we're going to provide three interesting math-related exercises where you and your students, or if you're a home hobbyist, you know, you're welcome to, see how various aspects of color and filters and light operate, you know, to give us the variety of things that we see and experience. I'm just going to throw in as a interesting comment, our sun is not a yellow star, it's a white star. Any photograph you take of the sun in space shows it to be white, not yellow. The reason that we have a yellow sun is because we're standing down here on the ground, and if you were to look at the sun when it sets in the horizon, it would look red. But if you look at it when it's highest up in the sky, like in the summer sky at low geographic latitudes, it'll tend towards yellow and even white. And that all has to do with the dust particles in the atmosphere, and there are fewer of them when you look straight up than there are when you look down towards the horizon. So basically our atmosphere acts as a color filter. It basically takes out a lot of the blue light from the sun and gives us a red sun at sunset. And as you get up towards the zenith directly overhead, there's less and less dust, and so there's less and less of the blue color taken out of the light, and so you get things that tend towards yellow and even colorless. So anyway, these are the standards that relate to the sun as a primary source of light and energy from the sun, where it's created, and so forth and so on. So there are quite a lot of places where sun and color and light sort of connect up with the standards. So, first of all, we have sunlight and the visible spectrum. Well, light is produced, is basically a consequence of particles called photons that carry energy. All right, the amount of energy that they carry depends on the wavelength. So photons that are very long wavelength carry very little energy, and photons that have very short wavelengths, they carry quite a bit. And so we can organize the energy of these photons and their wavelength along a kind of a linear line. It's redundant. And so we call that a spectrum. And typically, one might put the shorter wavelengths on the left-hand edge and the longer wavelengths on the right. And that basically is the gist of how you organize sunlight into a spectrum of wavelengths from short to long. But the thing is that there's nothing in this wavelength description of light that has anything to do with color. And that's for a very good reason, because color does not exist in the outside world. It's a complete artifact of how our brain processes information that it gets from the eye's retina. In fact, this is one of the interesting questions in neurophysiology and brain research is, where does color come from? And in brain research, they call this a qualia. So if you look up qualia on Google, you'll find all kinds of discussions about these perceptions that our brain has of the outside world and how it organizes information. Well, of course, one of the most valuable things about light and wavelengths is that some things reflect certain types of wavelengths and other things reflect other types of wavelengths. So you could look out in the world and you'll discover that things like ice reflect a particular collection of wavelengths. Things like water reflect other wavelengths. Things like plants with a lot of chlorophyll, they will reflect yet another group of colors. It turns out that there's a huge survival aspect to our brain being able to sort out these wavelengths. For instance, if you were to look at a distant hill and see wavelengths corresponding to chlorophyll, you'd like to know that those are the wavelengths corresponding to chlorophyll. So your brain wants to tag those wavelengths with some kind of a qualia that's distinct. If you're looking at water, that's also got a lot of survival characteristics to it. Water does not reflect light the same way as chlorophyll does. So your brain might want to figure out, where those wavelengths are as it looks out into the scenery around it. So that again has a big survival aspect to it. So, as your eye gets this flood of information, the brain actually tries to process it into survival aspects, like, am I looking at water, or am I looking at ice, or am I looking at chlorophyll, which for most animals, they like to eat things made out of chlorophyll, but they'd like to distinguish between chlorophyll and ice. They don't want to go as a herd marching off in the direction of where there's ice. That doesn't have very good survival aspects to it. So we get color from a combination of how the eye processes wavelengths of light and basically how our brain tags those wavelengths in a way that promotes survival and a quick read of the environment that it's seeing visually. So, as I said, the interaction of light with matter tends to favor some wavelengths over others, depending on what the material is. I gave an example of chlorophyll. Now I'm going to revert to talking about color. Chlorophyll basically reflects green light really well. So if you look in a distant part of the scenery and you see green, chances are pretty good that there's chlorophyll and plants over there. So as a herbivore, that's the direction you would like to go for lunch. It's also the direction that you want to go if you're a carnivore, because you figured out that you like herbivores for dinner, and they tend to congregate in places where there's a lot of green. So anyway, light interacts with matter in a way that depends on the wavelength of that light. And I gave an example here of dust in the atmosphere. As you look out at sunset towards the sun is producing light at all the wavelengths in the visual spectrum. But because of the way the light interacts with dust particles in the atmosphere, it will tend to scatter out from that white light all of the blue light and the shorter wavelengths. So the net result is that you get a lot of red in the light that you see from the sun at sunset. Where does that scattered short wavelength light go? Well, it goes everywhere around you, and that's why you have a blue sky, because you're seeing light from the sun that's the most scattered, and that tends to be at the shortest wavelengths, which we perceive as blue. So in one fell swoop, we've explained blue skies and red sunsets. And the idea that the sun is a yellow star comes from the fact that when we look at the sun at very high elevation angles, there's still plenty of dust in the atmosphere that we're looking through. And the light from the sun is losing some of its blue. So the net effect is that it looks yellowish, even at very high elevation angles. So, you know, the sort of mistake we make by calling the sun a yellow star, you know, is understandable under those circumstances. So, okay, here's the deal. I mean, light passing through a material will tend to pass certain colors and certain wavelengths and not others. A green filter works because the full spectrum of light comes at it from one direction. And if you're looking through the filter at that light source, you'll see essentially the green wavelengths promoted and transmitted through the material, but all the other wavelengths will be blocked. So that's what we call a filter. And we can design filters to block any wavelength of light that we want, even all the way out into the infrared and radio wavelengths. And similarly, all the way out into the ultraviolet, far ultraviolet, and X-ray. Astronomers use that technique quite a bit, because it turns out that different wavelengths of light tell you different things about how objects are operating and how they're producing their light. And that's valuable to know. It's like an object is transmitting its fingerprint for how it works into space based on how much light it's producing at different wavelengths. You can work backwards and figure out what kind of a light source it is. Filters can be designed to pass only specific wavelengths. In photography and in the human eye, we have red, green, and blue components, which the brain processes separately and then combines into a colorized view of the world. And that's really handy, as I said before, because if you're looking out into the world and you see a lot of green, that's good for plant life. And if you see a lot of red, well, that might not be so good, because red is the color of molten lava and it's also the color of dead leaves. So that's not necessarily a direction that you want to go. And blue, of course, is the typical color for scattered light coming off the soft surface of water. So in one fell swoop, you know, just looking at the scenery, you can sort of distinguish what places you want to visit for the next meal and so forth and so on. But the thing is that we don't just perceive red, blue, and green. Our brain mixes these together, you know, like the recipe for, you know, for a cake. You know, one part of this, two parts of that, five parts of this other thing, and you combine it together and you get something interesting. Well, in the case of the eye and the brain, what you get are different shades of colors. In fact, you know, the human eye can perceive several million shades of color, but I can only perceive basically red, blue, and green. I mean, my daughters and my wife, they put paint chips on the wall and tell me that these three paint chips are distinctly different. And I look at them and all I see is white. And they say, no, that's yellowish up there and that's greenish down there. So different people have different ways of perceiving color, and some are better at it than others. In astronomy, as I said before, we tend to take advantage of the universe producing light in different wavelengths, and we tend to focus in on those that tell us the most about how the object is working, how it's producing its light. And that's a valuable clue to understanding the object itself. This is an example of a multi-spectrum view of the sun. Now, the colors that you see here have been colorized by astronomers. And the reason is that if I were just to give you black and white images, one in each of these wavelength bands, it wouldn't look good artistically. Plus, and here's the kicker, astronomers colorize their data because the brain is really good at processing colorized data. So if an astronomer colorizes data, they're availing themselves of the full capability of the brain to look for patterns and relationships and contrasts, in a multi-wavelength image. And that's a very good thing for an astronomer and a physicist to be able to do when they're analyzing something. Here's an example. I mean, the sun looks very different depending on what wavelength you're using. The far left is what we see optically, but then as you go to shorter wavelengths in the ultraviolet and towards the soft X-ray, as we go to the right, you're seeing exactly the same scene at different wavelengths. And you'll notice even in panel number 2 that it doesn't look like the visual image at all. That's because the visual image doesn't include the wavelengths where this solar flare is the most brilliant. And that's a valuable piece of information because it's telling you that even though you have a sunspot there, the X-ray and ultraviolet light coming from that flare is basically invisible. And the only way to see it is by filtering the light and detecting it, in the proper way. So here's a simple problem, taking advantage of what we know about filters. Here's the layout of the question. This is a simple transmission filter problem, okay? You want to study the sun by using a filter that passes only the light from hydrogen at a wavelength near 656 nanometers. And so which filter should you do in order to make that possible? There are 4 possibilities here that I've included. You can create a filter that passes wavelengths shorter than 700 nanometers. You can make one that passes wavelengths longer than 450. You can create one that passes wavelengths between 500 and 700 nanometers, or you can make one that goes between 650 and 660 nanometers. I'll give you a few seconds to sort of come up with an answer on your own. Okay, if we look at possibility number A, letter A technically, wavelengths shorter than 700 nanometers. If I were to draw a line on the spectrum that you see here, unfortunately, most of it is hidden by this Zoom plaque showing the participants. Shorter than 700 nanometers, shoot, that's not going to work because it includes not only the line that we're interested in at 656 nanometers, but it also includes the ones at 486, 434, 410, and 397. So A is basically useless if all we want to do is isolate the light from that one line that you see there. Passing wavelengths that are longer than 450 nanometers, well, if you were to draw a line on that little graph there at 450 nanometers, it would be between the line you see at 434 and the one you see at 486. That means that that filter will pass the light at wavelengths longer than 450, which means it'll pass the light from the line at 486 and also the one at 656. So that means we've basically mingled the light from 2 different lines together, and so that's not going to work. The next one, passing wavelengths from 500 to 700 nanometers, well, that's starting to look pretty good, but that is such a wide range of wavelengths that in principle, there could be all kinds of other nasty things in the background that you're trying to not see that are going to be corrupting the image. So what you really want to do is to use D, which is a filter that only passes light from a very narrow range of wavelengths around the line that you're interested in studying. And so D would be the best answer for this question. Okay, so that's basically what I said. I mean, you could argue, well, 500 to 600 isn't too bad. Well, I could agree with you under the conditions where there isn't anything else going on the surface of the object except that one hydrogen line. But if there happen to be other elements present, they would also be emitting their lines in this part of the spectrum too. And you'd be getting all of their contaminating influences. So here's what you do is you create these very narrow bandpass filters that are only a few angstroms wide, so you can narrow in on specific lines from specific atoms that are in specific temperature and pressure and density states. So you use these lines like a thermometer, and if you combine the information from 2 or 3 lines together, you can actually work out not only the temperature of the region you're looking at, but also the density of the region. And also, by the Doppler shift, it's motion to and away from you. So that's kind of neat. Here's an example of narrow bandpass filters used between optical on the right and infrared on the left. And of course, you pick up young stars being formed in the infrared, which you basically don't highlight very well in the optical photo on the right. So that's why the Webb Space Telescope and the Spitzer Space Telescope and others like it are so valuable, because they allow us as astrophysicists to sort of focus in on only the light from star-forming regions which we're trying to study. You don't get the contaminating light from all the other stars that have already been formed and have been around for billions of years. Intermediate problem, UV filters and sunblock. Well, this has good connections to fashion, because, you know, for people that use fashion and try to get away with the minimum amount of cloth, you run the risk of increasing your exposure to ultraviolet light and the hazards of skin cancer and things like that. So, you know, talking about UV filters and sunblock still has an element to it, you know, that anyone in fashion could really appreciate as they're designing the next generation swimsuits or whatever else. Bandpass filters, UV filters operate this way. On the left, you see this little diagram. It shows 2 curves, one in black and one dotted. The black curve is the way that zinc oxide absorbs ultraviolet light. It doesn't absorb the optical light very much, and that's why it's very flat around 400 nanometers. But as you get to shorter wavelengths, it really starts cutting back on the UVA2 and UVA1 light that passes through the material. Titanium oxide does an even better job at much shorter wavelengths in the UVB region, which is really the region where you need to worry about skin cancer for any prolonged exposure. So sunblocks are actually designed, you apply it, you know, to your entire exposed surface area. And in this particular case, if you look at the graph on the right, for this particular compound, to get an SPF of 45, if you follow the line for 45 over until it hits the curve and then follow it down, it says you need a film that's about 20 microns thick on the surface of your skin in order to provide an SPF of 45. So the basic thing is, well, how much sunblock do I need to lather on my entire body in order to produce an SPF of 45? So the information that we have is the surface area of a typical human is about 1.8 meters squared. Bathing suit coverage is 30%, and the cream density is 2.4 grams per cubic centimeters. So from all of this, we're going to figure out basically how much sunblock you need. We start with this information, the skin coverage. Now I'm using 0.7 instead of 1.0 because I've just factored in the fact that 30% of this surface area is covered by cloth, leaving 70% exposed. So the total surface area is 1.8 meters squared times 0.7. So you basically get 1.3 meters squared of exposed skin. The graph says we need a 20 micron thick layer in order to get SPF of 45. So now what we do is we figure out what volume of liquid we need and those particulars. Volume is simply area times thickness, and we know the area here is 1.3 meters squared. The thickness is 20 microns, which is 20 times 10 to the minus 6 meters. So we get a volume of sunblock that's 2.6 by 10 to the minus 5 cubic meters. In terms of cubic centimeters, it's 26 cubic centimeters of sunblock that we have to put on our entire body, or at least the 70% that's exposed. Okay, the density of the sunblock is 2.4 grams per cubic meters. So we can now work out that we need about 11 grams of sunblock spread uniformly over the entire exposed skin area in order to guarantee that we have an SPF of 45. So that's kind of how you do it. If you look on the bottles of sunblock, you'll see some don't really reach SPF of 45, some reach a much lower number. That's because the essential compound that they have in the sunblock is at a lower concentration, okay? SPF 45 in a cream, this is the minimum amount that you need to put on your body in order to provide SPF of 45. You can put more, but you can't put less. If you use a different material, a different sunblock, you might have 22 or 32 grams of sunblock on your skin, in the same way. So sunblock, UV filters, and SPF all go together, and they all act to block the ultraviolet light, from the sun.
Hey, Sten.
Yep.
It's Christina here.
Yep.
We have some interesting questions about sunblock that I wanted to stop you for, if you don't mind.
Oh, okay. This is a good time to pause.
This is a very interesting problem. I've been thinking about it myself. So one question is, I thought sunblock needs to be reapplied throughout the day. Can you address that?
It does, because a 20 micron layer of sunblock can basically be wiped away just by harsh language. So, you have to keep reapplying it or apply it at a pretty goodly thickness. It really all depends on the composition of the sunblock. Some are more reactive with water than others. Zinc oxide, long time ago, you used to have to lather yourself with zinc oxide. And when you went to the beach, you would see people that had this layer of white powder on them because the emolument that kept the zinc oxide in solution basically evaporates, leaving behind the white zinc oxide as a deposit on your skin. With modern sunblocks, they use organic compounds that are just as effective as zinc oxide, but when they dry transparently to the optical light, so you don't see them optically. But if you were to look at somebody with ultraviolet light, they would turn completely dark because the block would basically not reflect back out the ultraviolet light shining on the person. So, it's a kind of an interesting physics problem. And I probably massively oversimplified it, but I've only got 10 minutes to talk about the problem.
Sure, a couple more. So,
Sure.
would the amount that we're talking about in that problem be about a golf ball size amount of sunblock?
Yeah, it'd be about that much. Yeah.
Okay.
We're not
Good job,
talking, gobs of it.
Patrice.
We're talking about a golf ball or at worst, a baseball volume size.
Okay. And then also we can assume that a lot of swimwear is naturally, or not naturally, but it's UV protectant, either because it's polyester or double layered. But can you speak to that UV protective fabric?
Well, that's an interesting question. I don't know what the ultraviolet transmission of various types of cloths and materials are. I'm sure there's a range of transmission, even depending on what the material is. So they're not perfectly opaque to short wavelengths. So you've got to be careful.
Yeah, I mean, I know if you're close to the equator, certainly I've been burned through a cotton shirt.
Sure.
And that's why and then when you go outside, you wear those kind of surf shirts, which seem to be better at protecting your skin.
I mean, as a geek, I would probably go around with, swim trunks that are aluminum foil. That would match the aluminum foil hat that I would also be wearing.
You would look very cool. Yeah. And Patrice just wanted to add one more thing. She's very interested that some of these new fabrics are very tightly woven, and so that might be more UV protective as well.
I don't know if the weave makes that much of a difference, because it all has to do with the UV transparency of the fiber itself. All right.
Interesting.
I'd just like to jump in really quick because my chemistry teacher, today we were actually talking about like wavelengths, and we did an experiment with these UV changing beads, and we
Yep.
had a control group that we would put in the sunlight, and then we also had a group that we would put through different filters.
Uh-huh.
So like we had like transparent plastic, we had glass, we had
Mhm.
opaque plastic, and we also had an experiment where we did I believe it was 15 SPF and 50 SPF, and it was
Mhm.
interesting to see just how quickly when you turned on that UV light, the color immediately changed
Yep.
into like the bright pink that it was, but with the SPF like 50 or 15, it took a lot longer to even like get a slight color change out of it. And when I was doing the opaque experiments, we had like a piece of opaque plastic.
Mhm.
The color of like solid white just didn't change at all. So I think that maybe we should all just start wearing plastic everywhere. I'm not sure if that'd be good for the environment, but I think it'd at least protect our skin.
Yeah, that's a good point. It's interesting. Plastic is very rich in hydrogen atoms, and that makes plastics very good for radiation shielding. Believe it or not. So it's people are looking at spacesuits that have a lot of plastic in them. Unfortunately, the plastic that's the best for radiation shielding, which is even shorter wavelength than ultraviolet in some areas, is very brittle. So it's a real challenge to sort of check off both of those boxes to make a spacesuit that's got good radiation shielding made out of plastic, and also one where you could actually move around without cracking and all of that stuff. So anyway, yeah, interesting problems.
Yeah, great. I'm excited to hear that student was experimenting with UV beads. That's really cool.
Yep.
And of course, what brings to mind is that polyester is really a type of plastic. Um, so that, makes sense as well. Okay, thanks, Sten.
Yeah, you might also consider getting a black light, a one of those fluorescent tube black lights, and smear half of it with a sunblock and let the other half remain, open and untampered. And basically, what you'll see, I think, is because the ultraviolet light from a black light, it's ultraviolet light. If it's short enough wavelength, the sunblock should basically turn that part of the black light completely black. I mean, it won't transmit any of the UV coming out from inside the bulb, but the other half of it, you'll still see and be able to affect things from the ultraviolet light coming out from the sunblocked part of it. I haven't done that experiment. I mean, it should work if the UV light is of short enough wavelength that the sunblock can actually block it effectively. Oh, all right. Well, that was kind of fun, wasn't it? I'm going to kind of breeze through this next one. Opacity and color are related together in an interesting way. Opacity is sort of the degree of transparency of a material as light passes through it. And in physics, we sort of express this by it's an exponential function, and the exponent depends on essentially the absorption coefficient times the thickness of the material, which in this case is x. Absorption coefficient changes depending on the material and the wavelength. And x is basically the physical thickness of the object, whether it's a pair of sunglasses or the radius of the sun, x doesn't care. So what we're going to do now is, you can also express this function, which is called Beer's function, I think, in terms of what's called the opacity, which is given by the Greek letter tau. So high opacity materials, things that are really opaque, well, it makes sense that they're not going to transmit very much. So in this case, if tau is a very big number, that initial brightness, which is I0, is going to be cut down enormously, so that by the time the light gets a distance x, there's going to be almost none of the light left if the opacity is very high. Now, we can look at for instance, two different materials, for shielding or blocking light. Suppose we have one material that has an extinction coefficient of 0.35 per centimeter at a wavelength of 300 nanometers, and another material that's 0.05 per centimeter at a wavelength of 800 nanometers, a bit longer in wavelength. The question is, what percentage of light at these two wavelengths will remain after passing through 1.5 centimeters of a filtering material? Okay, at this point, I mean, you're welcome to sort of fall asleep. This is a kind of a technical extension of the idea of a filter operating at different wavelengths with different amounts of opacity depending on the wavelength. And all of that is carried by this absorption coefficient K. K is very small at the longer wavelength, and it's very large at the shorter wavelength, which makes sense. We just talked about things that absorb ultraviolet light really well at short wavelengths and don't absorb it very well at longer wavelengths, so you can actually see things. You can actually see the skin of somebody that's slathered with sunblock because the K value in the visual part of the spectrum is very low. K value at ultraviolet is very high. That's why it's an ultraviolet blocker. Well, if we ground through the math, we used our Beer's function. Here's what material number 1 would look like. The K is 0.35, the width is 1.5. So if we multiply those together in the exponent, we get minus 0.53, which is what we call the opacity, the tau, all right? And if you then use that as the exponent for a natural function E, you get 0.59. And so 100% times 0.59 is going to be 59%. That means 59% of the light that entered this thing makes it to the other edge and transmits. Okay, so it has a transmission of 59%. At the shorter wavelength, again, we do the multiplication, 0.05 times 1.5. This time we get an opacity of 0.075. So very little opacity means that it's going to transmit most of its material. And by gosh and by golly, if you do that last line, it transmits about 93% of the light through its 1.5 centimeter thickness. If we compare the two, the light at 300 nanometers will transmit 59% of its initial brightness, so it blocks 41% of the light at this wavelength. For light at 800 nanometers, it transmits 93% of the initial intensity and absorbs 7%. So this allows you to sort of compare two materials as you're trying to design a good filter. The thing that you have to mess with is basically the opacity coefficient K. And that's something that you determine either at the lab bench by mixing organic compounds in different ways, to get different opacities at different wavelengths. And that's sort of all there is to it. This is also telling us something really important about looking at things in the universe, that basically, if you're looking at things at 800 nanometers, chances are you're seeing most of what's there and only losing about 7% of the light from that object if it's going through a material that we just described. Whereas if you're looking at the same object at shorter wavelengths, that material in between you and it, might be so opaque that you basically lose most of the light you're trying to study. So that's sort of how it all works. And so now you've got basically 3 different problems, 3 different levels. And so that's the end of the presentation. And next time we're going to talk about experiencing the sun. That's the theme for March 2024. And we'll be talking about basically solar storms.
Hi, Sten. We have some more questions.
Yep.
If you don't mind.
Yep, I'm going to do the stop share.
Okay, the last problem. Here's a question.
Yep.
Would it be possible to synthesize a material such as an alloy or a mix of other materials that block every form of radiation? If this is a possibility at all, or is it impossible due to the chemical reaction that occurs between elements?
That's a wonderful, wonderful question. There are practical limits to creating what you're calling a broadband filter. When you get a range of wavelengths in your filter that's more than a factor of 10, you can't sustain the material or the technology beyond those limits. You have to do a different technology. For instance, organic compounds might work well to create blocking filters in the visual band, which goes from about 400 nanometers to 700 nanometers. But those same organic compounds will not work to block radiation at shorter wavelengths or longer. You'll have to use either a different technology than filtering, or you'll have to use inorganic substances or other types of materials. In radio astronomy, we use interference filters where, well, I'm not going to get into all the witchcraft that goes on there, but you can't really create a broadband filter that's working over wavelengths that differ by a factor of 10 or 100 from one edge to the other. You have to use different technologies in each decade range.
Great. And one more. Additionally, I thought that gamma rays were one of the stronger forms of radiation. Where do the neutrons fit and how do they pass through more objects? Can they be part of radiation?
Neutrons are not electromagnetic radiation. They're part of a different spectrum we call the particle spectrum, which includes cosmic rays, neutrons, protons, electrons, dark matter, if we can ever detect it. Gamma rays, they're a different form of energy in the electromagnetic spectrum, and they basically pass through just about anything, except lead or something that has a very high density. The reason that neutrons pass through a lot of things is because they are electrically neutral. So when they collide with things, they basically collide as though they were billiard balls. They don't collide as though they were electromagnetically charged particles, which would make them look a lot bigger, as things that are barreling through a material. So neutrons, they pass through a lot of different types of shielding materials with relative ease.
Great, thank you. And feel free also to unmute if you have any questions for Sten. I know we have a few extra minutes here.
I have to unmute people, so I can certainly do that.
Oh, sorry about that. I thought you already did that. My bad.
I think I have on the screen the QR code, and I've also put the link for the folder in the chat a couple of times, or in the Q&A, but I'll do that again. Patrice asked for it, so that gave me a chance to answer it. But you could repeat that too, just as from the last response. But let me go back, let me get out of this, and then I can go back and unmute more.
Some really great questions. We have a lot of thank yous in the Q&A to you, Sten.
Very cool.
From Patrice and from the anonymous attendee who also had some great questions.
So basically the bottom line is that you just spent 45 minutes taking fashion advice from an astrophysicist.
The best.
Yeah.
So.
I thought it was really interesting about the evolutionary aspects of seeing color, finding food and things like that.
Yeah.
I never thought about that before, so that was really cool.
Yeah. Yeah, it's evolution plus chemical variation combined, boy, give you all kinds of amazing things in the world.
And also, this is also really reminding me that I need to wear my sunscreen, because I have a horror story about UV radiation, because I went to a track meet last year when I was a freshman, and I didn't wear sunscreen. I was 6 hours, bright blaring sun. I didn't wear any sunscreen. My mother was not happy to see me come home, red shoulders, and I had a uniform imprint on me, I think, until like winter started. It would not come off. So I think I learned my lesson, but I was also just really curious about the fact that neutrons pass through a lot of stuff, because when I was in biology, we were talking about how some particles and matter passes through, because cells are semi-permeable, and we were learning about how things go through. And it was interesting just to see, because neutrons aren't charged, that might also be part of why certain chemical, certain matter, like water, passes more easily through those cell membranes. So I just wanted to connect it back to even biology, which I know isn't related to physics, but I thought it was just a really cool cross-science reference.
Yeah.
It is. Thank you, Olivia. And I ran track in high school, and you wear sunscreen, girlfriend. You really do need it because
I
otherwise.
learned my lesson, don't worry.
And it's interesting that they're learning how to do it properly so that, it really actually works. And then, as we were discussing earlier, the clothes are great. I mean, the surf clothes have really done amazing things for us fair-haired, fair-skinned people in particular, because we don't have a lot of
Yep.
melanin.
I
Yeah,
struggle with the fair hair
when I
thing.
was 7 years old, I went to the beach and I didn't use sunblock, and I was out on the beach in Santa Cruz for about 3 hours collecting seashells. And when I came
Oh
home, I
no.
basically had first and second degree burns over my entire body with blisters. And basically, I was radiation poisoned because I was throwing up a lot.
Wow.
And my
Oh
mom
my
slathered
goodness.
me with Noxzema. And to this day, I cannot stand the smell of Noxzema because it's such a painful flashback.
Yeah.
And of course, the other benefit to having been toasted like that when I was 7 is that I've had like 3 basal cell carcinomas removed from my body in the last 20 years. So, yeah, it pays to be aware of sunblock, now that we understand how it works.
Look, now that I have the equation to figure out exactly how much sunblock I need, you bet I'm gonna be bringing I'm gonna bring a kitchen scale to my meats and measure it out. Don't worry.
So Greg, you had a question? I think if you unmute yourself, I have you unmuted in my list. Can you unmute yourself? Because that's what my screen is showing you need to do.
A typical disclaimer that physicists put into solving any problem is that the answer to the problem is probably good to within a factor of pi. So,
So extra, you're saying extra.
yeah, so feel free to either multiply or divide the answer I gave by pi just to be on the safe side.
I think I'll stick with multiplying. I'm not dividing
Okay.
anything at this point.
That has very good survival attributes to it.
So Greg, do you want to jump in? You were talking earlier. I'm not hearing you. I see your hand. I'm going to ask you to unmute. Yeah, this was great, Sten. Very interesting.
Thank you.
Anybody else have any questions?
So maybe I missed it. Stan, if you don't mind, just remind us what you do. You're a physicist, you teach physics, you research, what's your research area? This is Patrice, by the way.
No, I work at Safeway and I bag fruit for customers.
Fabulous.
Yeah, yeah.
How come? I
I'm
like
working,
apples and
I'm
oranges.
trying to be flexible in my old age. No, I'm a card-carrying astrophysicist. I worked in infrared astronomy for many years, and then I moved over to space weather, and that's where I am now. And I love writing about cosmology, which is actually my first love. I don't expect to get too many cosmology questions in a series on heliophysics, but
Okay,
that's fine.
fabulous.
Hi,
Thank you.
So Patrice, can you see, I just put his bio up. Can
I
you
did.
see?
Thank
Oh,
you.
Okay.
God, that thing again.
I
And
must
this-
have missed it.
and-
Thank you so
And
much.
this is in the Google folder too, so
Great. Thank you.
you're welcome. Thank you for asking. He's amazing.
And
Can I ask for-
please buy my books. I'm trying to get a new roof put on the house in the
I
next
got
year.
you. GoFundMe. Understood. Yeah, fundraiser. Understood.
Can I
Thought I would
jump in really
sneak that in
quickly?
there. No.
Look, I'm all here for self-promotion. Really curious, what is like the big difference? Because I know heliophysics is central on the sun. Cosmology, is that just like a general term, like an umbrella term for so different things, or is it like the study of other cosmic bodies?
No, it's the study of the origin and evolution of our universe using galaxies as test particles. So the smallest things we pay attention to are galaxies. So that's why for myself, my transition from working in cosmology to working in heliophysics was such an abrupt change, because I had to reassess my entire scale of the universe that I carried around in the back of my head. Anyway, an interesting challenge, but I did it late in life. So, old dogs, new tricks kind of a thing.
So heliophysics would then focus more on like radiation particles, solar flares, and all of that. awesome stuff.
It would
And
focus on the interior of the sun, the production of magnetic fields in the subsurface, the phenomenology of the photosphere, flares, sunspots, faculae, and all that, properties of the corona, origin and evolution of the corona and the surface of the sun, plus the process of the emission of the solar wind and its reach out into interplanetary space. So it covers a radius of about 120 astronomical units from the center of the sun in, all three dimensions. So it's a pretty big volume of space.
Okay, one last thing before we run out of time. Can I ask what the solar wind is? Because I've heard some different terms for it, but I've heard it's like particles coming out of the sun. I've heard a lot of different things.
Yeah, Olivia, don't go there. Actually, no, the solar wind is just basically the emission of plasma from the upper atmosphere of the sun, and it basically flows freely into interplanetary space in all directions, except along the exact poles of the sun, where the solar wind is not very strong at all. So it's a flow of charged particles from the sun that escape the sun. That's all. That's all
Amber,
it is.
Amber has a question.
Yeah.
Can you unmute yourself, Amber?
What's your favorite part about learning?
Your favorite what? Say it again.
Part of learning about space.
Your favorite part of learning about space, Sten. Did you get that?
I mean, I've just been, since I was 10 years old, looking at the night sky. I mean, my brain just simply could not figure out what it was that I was seeing. And it was so big, so different, so immense. It's every day during the daytime, you see trees and animals and birds and stuff. And then when the sun goes down, you see the blackness of space and you see stars. It's like the transition is just, to me, so striking that I still haven't been able to figure out what it all means, in terms of the scale of the universe and, why it is that we're here thinking about it all and how amazing that is. I mean, it's just a whole, like my astronomy professor at Harvard used to say, it's a dog's breakfast of all kinds of lovely things.
Greg, did you want to have the last question? Your hand's up again. Can you unmute yourself? Gosh, I'm sorry. I wish I knew what was going on. Do you want to try putting your question in the Q&A? Nope, I don't see it. So Lloyd had a question in the Q&A. Have other species besides humans evolved in some way to filter UV light to protect themselves?
Oh yeah, that's one of the first things that animals that live on the land do, because UV light is a hazard. Before we had oxygen in the Earth's atmosphere 2.5 billion years after the Earth was formed, I mean, we just had basically ultraviolet light getting all the way down to the surface, and land masses were completely sterilized. It's only when we developed an ozone layer, through the production of oxygen as a byproduct of certain types of plant systems, that all of a sudden there was enough blockage of the UV light that organisms could sort of crawl up onto the land and start evolving into, things that live on the land. So, and that's why we have, the Cambrian explosion and, all of that ensued after that. So, yeah, I mean, the whole subject of ultraviolet light in the history of the Earth is a very, complicating factor. So, yeah.
Okay, thank you. Another one is HEAT, H-E-A-T, that's us, Heliophysics, doing any work with sonification?
Well, I think, Hillary, Christina, you could answer that a lot better than I. I think the answer to that is we are not directly doing it, but we're promoting groups that do, I think.
I'll let you answer that one in the chat, in the Q&A. Go on to another one. Will you be studying anything in particular during the April 8th eclipse?
No, I'm going to be on vacation up in Vermont, so I hope to see it. For myself, I've been studying, why it is that the ancient Egyptian civilization didn't really note all of the total solar eclipses that passed across the Nile during 3,000 years. So I'm kind of interested in the ancient history of eclipse sightings by ancient civilizations that should have seen them, but never seemed to record that they did. So it's a real puzzle.
NASA will be studying the corona in a lot of different ways, and over the duration of the eclipse, over the space of the eclipse. I put a note in there. I can't quickly get that link, but Christina, you have it because you have it in your slideshow tomorrow. You have to come to Christina's webinar tomorrow.
Yep.
And we also like to study the ionosphere
Yes.
under the shadow of the moon. Because somebody had a great question about solar wind earlier. That solar wind interacts with our ionosphere and it can disrupt our communication signals. And so that's one of the reasons we're very interested in studying it during the eclipse. And the total solar eclipse was the only way that folks could study the corona way back when. But even to this day, even though we have all these fancy instruments from NASA, we still wait for these opportunities to make unique observations. So it's really exciting.
And also Christina and Stan will talk tomorrow about some of the missions that are studying the sun, the most current ones like SOHO and STO and Parker. And Parker will get the closest to the sun, its closest point to the sun in December. So Sten will be doing a webinar on that because that's a very big deal. We have never been so close to the sun with our instruments. So.
I'll be doing that live from the Parker probe.
Yay.
Yeah.
All right. Did we cover the other questions, do you think? Christina, are we good?
I think we're good. We have a lot of thank yous and appreciations.
Oh, great. Glad you enjoyed it.
So, yeah, and I think you have our contact information. So if you have any other further questions, we can always follow up.
Yes, and I will send, I captured all the questions and answers that I could, and I put the link to the Google Drive. And then I'll send to everyone who registered. So even if you have someone who registered, but they couldn't come, they can listen to the recording. Also in there is the registration link for next month's webinar. Sten, what's it on?
Basically, solar storms, coronal mass ejections, flares.
Okay, so I see Olivia logged off, but I bet she comes back.
Oh, don't worry, I'm still here. I'm gonna be there next month.
Okay, great.
Cool.
From your friends.
I'll see if I can. I'm the resident space nerd in this town, so I'll see if I can find someone.
It only takes one to encourage other people and get them excited.
Yeah.
All right. Well, thanks, everyone.
Okay. Thank you.
Bye-bye.
Thank you so much. Have a good night.
You too.